Good evening and welcome to a Smart Space live Q&A. My name is Curtis Brown. I'm your host this evening, and I'm here with John Urschel, one of my math heroes, and certainly just an all-around good guy. For those of you who don't know, John is a former NFL football player, and he's currently a student, a doctoral student at MIT. Pursuing a doctorate there. And John, I'm super excited that you've partnered with us to do these videos, and we had a good time doing them. It was a good, exciting set of videos to make. But before we kind of dive in, I want to go ahead and just dive in. But before we do that, I want to give our people out in the audience a chance to chime in, one, with where you're watching from. I think that'd be kind of cool to know. And then secondly, I want to encourage you, as John and I kind of go through this conversation, this is a live Q&A. And so it's not just supposed to be me asking the questions. We'd love to have you guys asking John questions, both about the geometry topics that we talked about in the videos, and then as well as just generally questions for John, I think would be interesting to have come in. So go ahead and put those in the chat, and we'll monitor those. But to get us started, John, I thought maybe if you'd be willing, could you talk a little bit about the connections that we were trying to make between similarity, congruence, and transformations, and kind of that whole group of things together? How did we and why were we trying to do that?
Yeah, Curtis, thanks for having me. First of all, I gotta say, I really enjoyed making these geometry videos. Like this was really fun. It sort of like brought me back to, some really cool math that, I remember from my childhood. And if those of you who are sort of watching on YouTube or in the chat, if you haven't seen the videos, you should check them out. They're freely available on YouTube. And Curtis and I specifically went over certain geometry topics like congruence and similarity. And we sort of put a very algebraic spin on these things. So, when you're earlier on, you first learn congruence and you think same size, same shape.
Right.
You learn similarity and you think, same shape. And you come to start to appreciate how you can really think about these things more rigorously when you all of a sudden take a geometric object, like a triangle or a square or whatever it may be, and thinking about it as something in the plane.
Right.
Being able to quantify what does same size, same shape mean, and being able to connect those things via things like rigid transformations if you're talking about congruence, or if you're talking about similarity, rigid transformations plus dilations.
Yeah, John, it was kind of a fun realization for me watching and thinking about. In middle school, we talk about transformations, we talk about congruence and similarity, and we see that same size, same shape thing. And we have, a lot of times kids will have a problem where they've got, one single shape over here. They're calling the pre-image, and then they'll have 4 or 5 of the others over here, and they have to pick out the one that is similar or the ones that are similar, and if there are any that are congruent. And they kind of just mentally, I think a lot of them do what you and I ended up doing algebraically and then on the plane in geometry, by following some rigid transformations, defining those, being able to take a pre-image and map it to the image via reflections, translations, rotations, being able to kind of work through all of those pieces. So I think that was that was fun for me to just kind of move that up into geometry and use our geometry, like our high school geometry, to do what we had already kind of been doing in middle school. So that was kind of fun.
Yeah, no, I think it's pretty intuitive, and it's a way to really sort of connect rigid transformations with the idea of congruence. Because, okay, suppose you have 2 shapes just sitting somewhere in the plane. If you want to show that these 2 things are congruent, what you want to do is you just want to put one on top of the other. And so what do? Well, if you imagine that these are on 2 sheets of paper, first you sort of move one sheet of paper closer to the other.
Right.
This is your translation. And, maybe they don't they aren't oriented the right way. So maybe you have to flip a piece of paper over. This is your reflection. And then you got to make sure they line up, and this is your rotation. And so it's sort of, I think that when you cover these things, it's really important that you ground yourself in a really intuitive sense. And then these concepts like reflection and translation and rotation become very natural.
Yeah, that was fun. That was fun. So John, on the order of connections and things like this, it's important. I think we saw, doing this kind of algebraic connection to what we saw geometrically and kind of conceptually what we used to do in the middle school, and doing that a little bit more formally in the high school. So why are connections like that? And you can talk about other math concepts too, if you'd like. Why are connections like that important for students to be able to make?
Yeah. So first of all, I'm going to sort of not at all touch on the fact that these rigid transformations are actually quite important at higher levels of math. That I'm going to sort of leave somewhat aside to not sort of get into more complicated things. But I want to say that just taking this as an example, I think anytime you're covering some subject in math, you should always, okay, I'm not sure always, but I think almost always you should really try to focus on intuition rather than sort of memorization. And so just, as an example, when we were talking about congruence, when we're talking about these rigid transformations, yes, you can write down the formula of a rigid transformation. You can write down the formula of a rigid transformation. You can write down the formula of a translation, of a rotation. Rotation's a little more complicated. Reflection formula is quite complicated. You can write down these formulas and sort of like learn to recognize them. But more important than sort of learning these formulas is to be able to intuitively understand what each of these things are doing, and sort of why these things together can show two shapes embedded in the plane are congruent or not. And for instance, I don't think we touched on this in the videos, but like one fun intuitive exercise is the following thing. So if you're watching, you might enjoy this. We talked about showing two things are congruent by doing translations, reflections, and rotations. I'm curious, you can try to think about this at home. You don't need to answer now. Do we need all three to show the two things are congruent? You can show that all rigid transformations can be sort of represented as a composition of these three operations. The question is, do you actually need all three of these operations, or can you, let's say, represent any rigid transformation just using rotations, or just using reflections, or just using one or two different things? And how many times do you have to sort of use it? It's sort of a fun, intuitive exercise that gives you sort of a better sense of how these things work.
I like posing that question to the audience. So I'd love to hear as we continue our conversation, maybe some people comment in the chat about that. So John, as we did these smart space videos, and just a reminder to the people out there, they are up on our YouTube channel. The playlist, the link to the playlist has been put in the chat already. You can also find them on education.ti.com. You can navigate to our through our page and be able to find them there. So you can check those out. But I'd love to hear what other people have, if they think that maybe we could just live with only rotations. Maybe we could just live with only translations or only reflections. It would be interesting to see if anybody can kind of think through that, and if they have a reason maybe why they think that.
Yeah. So, one sort of cool sort of related thing about thinking your way through that is to ask yourself the question, if I have some rigid transformation in the plane, how many non-collinear, how many points in regular position, which means I don't want 3 points on a line, let's say. How many points do I need in the plane to sort of know where those points map to before my rigid transformation is uniquely defined. That's also like a fun related question.
Oh, wow. Yeah, that's a really good one.
But like when I say how many points, make sure that these points are like in regular position, which means, okay, if we're in the plane, we don't have like 3 points on the line.
Okay.
Like so that's a fun question, I think.
Okay, so unrelated to the topic we're on right now, I've got a question that came in just now. John, this is like specific to you.
Okay.
So number theory,
Mm-hmm.
topology, combinatorics, algebraic geometry. Could you rank them in order to how much you like them?
That's a great question.
This is from
so hard.
Pankaj Partha. I'm sorry,
Okay.
I probably butchered that, but
let me think. So this is a good question. I'm gonna say I really like combinatorics. I really like combinatorics, especially these sort of like enumerative type combinatorics, because the problems are so easy to state. Like any enumerative combinatorics problem, well, not any, but a lot of them, you can state to someone on the street and they'll understand what the problem is within 60 seconds. But some of these problems are extremely complicated to solve. And it's a field where I think people have to be really, really sharp. And this is like combinatorics is a field full of like some really sharp people with a lot of good tricks. Often they're, former like Putnam fellows and things like this. And so I have a lot of respect for people in that field, and they come up with like these beautiful solutions. Number theory is also really good. Topology, I never got too far with topology, just because at some point in my life I became more of an applied person. But I really enjoy, like when I first learned about point set topology, I thought it was like really cool stuff. And algebraic geometry, I've never really gotten into, just because sort of I shifted from pure to applied math right around when I was like my last year of my undergrad. And so I never really got to like high level algebraic geometry. Although these days I do actually find myself like learning about these things some, and like using these things some, like these, I'm going to butcher these things, by like these nulls Stellenstats. I'm going to butcher it, but I know how to write it. But like these sorts of things are really, really cool results from algebraic geometry that are like useful in applied areas.
So if I had to answer that question, I think I would also answer combinatorics, but only mostly because kind of the same reason you answered that, in that it's familiar. If I walk down the street, I can ask a question or pose a question to someone that maybe the result, or how you might compute the answer to the question is extremely complicated, and yet there's a pretty simple way that you can state it. And often
deceptively
it's
simple
questions that people are interested in knowing. Right? Is how many ways can I do such and such, or how many combinations are there of this, whatever.
Or how many balls can I pack in this like area? Yeah. Deceptively simple is what I would say. Yeah.
Right. They're deceptively simple in the way that we state them, and extremely complex in the way that we solve them. So I think that, and they're interesting, and I think they hold people's attention often. And on that note, I think it's also, maybe we can move to another question or another topic that I had for us, and that is that we've talked a little bit about interest and engagement here. So do you find that like meaningful connections for students, like thinking about how it relates to the world, or maybe how it relates to something that they're passionate about, is that important for students to be able to find? Does it help them with understanding and learning mathematics? And is it important just in how they interact with the world? Maybe those are three questions, but
yeah, I'll take like some combination of the three. I would say when you're learning math, it's really important that it's grounded in something that you care about. And I think when math is sort of just taught or done in a vacuum, like you can lose some people except those that love math for math's sake, which I can say, myself, I'm someone who was really interested in just like understanding math for sort of like the pure puzzle of it. But
Sure.
I would say that, our connection with math as people is not really in a black box. I mean, when you think about the earliest uses of mathematics, like the earliest recorded uses, these are all for practical purposes. And I would say, at least early on, the majority of sort of mathematical discoveries sort of happened in some narrative for some reason. Like these things were not discovered in some vacuum. And I think that sort of understanding the context and the humanity of mathematics actually is like a really helpful thing. Like for instance, this is a random example that for anyone in the chat who like maybe majored in math, I can tell you that as an example, like the first time you take a class in measure theory, it's not at all obvious to you why you're sort of learning the things you're learning and why you're doing the things you're doing if no one sort of starts off by explaining to you that like at some point in history, mathematicians had a little bit of a crisis because people were coming up with functions that they couldn't use Riemann sums for to get sort of an answer for an integral. And when you sort of learn the context of why something sort of came to be, it really helps sort of like influence your understanding and your appreciation of it, I feel.
Okay. Yeah, that's true. It's very true.
Yeah.
So I just, I was thinking about this same, something similar to that, and thinking about, I've been playing with looking at the COVID-19 data for different countries around the world, and just trying to connect experiences and things that are going on in that part of the world, and the rises and falls in daily cases, and just being able to connect those two things together and see, just wow, this is really kind of cool. What kind of interpolations can we make? What kind of interpretations can we make about what's happening, and are these two things related? Is it totally unrelated? All that kind of stuff is interesting to me. And I think, as we get to talking to students and trying to get them to engage with mathematics, it's important to understand that mathematics really help us understand the way the world works, right? I think that's super, super important for them to know that, a lot of the mathematics that we do and a lot of the mathematics that we learn, especially, in high school and a little bit beyond, are things that help us engage with and understand the way the world works, right? And describe the way the world works. I think those kinds of things are really important for students to understand, to be able to look at some collection of data of CO2 from some volcano in Hawaii, and look at the fluctuations up and down, and be able to connect that to the fact that the earth breathes throughout the year, right? And see that there's an up and down pattern to that, is important. So all those kinds of things are important. One, to understand the world, but two, to be able to make it foundational for them and connection, some sort of emotion for them to learn it.
Yeah, absolutely. I mean, math it's the sort of, this is like the quantitative language we use to sort of like talk about and understand the world around us.
I've seen someone actually talk about, actually what's on my shirt right here. And how we developed this set of information, looking at trigonometry, and really the study of triangles, and that thing came from really the study of circles. And initially, all of these things came up from people trying to describe certain properties and things about circles. And then they started to realize and notice some of the things that are happening some of the things that were happening were really all related to triangles, and so we took this what you might have called circleometry and turned it into to trigonometry and talking about triangles. And so it's kind of I've seen somebody talk about that, and it's pretty interesting stuff. I have a person here that commented that they're going to switch to mathematical studies after unsuccessfully attempting a physics degree. I just, I think that thinking about the connections in mathematics, physics is a lot made up of that, right? How we can describe the world.
Okay, sort of. I'm gonna watch my language in case there's some physicists watching. I don't want to like take too much credit for I don't want mathematics. I don't want to sort of like give mathematics like too much credit, and perhaps in some people's eyes. But I would say that no, I mean math is really sort of the foundation. It's like a really key foundation for understanding a lot of things in physics. And I can actually say that my first ever research project, my first paper, was actually a physics problem.
Yeah.
And so it was a three-body problem. And we came to understand certain things about this specific three-body problem we were looking at through mathematical analysis. And I would say, if you like physics, if that's something that you're really interested in, and it's not necessarily, it doesn't feel like it's sort of going your way right now, when you sort of train yourself mathematically, you can really solve a wide range of problems. And I would tell you that if you're interested in physics, you get an undergrad degree in math, maybe you stay close to physics, you take your mathematical physics classes, you take, your quantum mechanics, your relativity, some things like this, you take a classical mechanics class. You can always try to sort of do your PhD. If you want to do a PhD in mathematical physics, you can get a master's in mathematical physics. You can try to minor in physics, and people will still look at you like you're a well-trained physicist because you have a strong math background. And so right. I wouldn't sell yourself short. There's definitely a path to sort of staying close to physics while in math.
Wholeheartedly agree with that. John, we've got a little bit of time left, and I've got some other things here. A comment by Kelly Corrigan that says that, it's so cool that the math that was developed and then applied was often developed, a long time ago, and then applied hundreds even of years later afterwards. I think that's really kind of a cool thing. And so I totally
yeah, absolutely. I mean, it's this is a thing you see all over math. Someone discovers something interesting, and people look at it and they say, oh, that's cool, you discovered that, but what are we ever going to use that for? When is that ever going to be useful?
Right.
And then however many years later, whether it's 20 years later or 50 years later or 100 years later, this is an extremely popular thing and is a foundation of some field. This happens right. all the time. Yeah.
It does. It happens. And that's always so cool. So this is cool. Could you talk a little bit about the most difficult situation that occurred while you have been teaching? I know you teach,
while I've been teaching, let me think. Okay.
And it could be like a student relation thing, or how you student, or
I don't think that's a question that I necessarily want to answer, because
fair enough.
When you teach, you sort of, I don't know how to put this, but I very much respect my students' privacy, and so I can think of a thing or two that was sort of particularly difficult. Often you have a class and your students are people, and students have troubles outside of the classroom, and I think that any teacher who has taught for any period of time is sort of familiar with this. And as a teacher, for me as a sort of college level teacher, which is sort of even more detached than high school or middle school, you have a responsibility to those people, where if they're struggling with something sort of in their lives, you want to try to, help and support them and make sure that, your class doesn't sort of cause more issues. But I would say in general, outside of sort of students, struggling with certain things, sort of teaching has always been like an absolute pleasure for me.
That's awesome. And that's totally true, right? I won't take this any farther than you did, but I think, yeah, outside struggles, things that students are dealing with outside of my classroom, have often been the most difficult things for me to deal with as a teacher, because of things outside of my control, outside of their control, that are affecting them from outside the classroom. I think that's often one of the most difficult things to deal with. I've got another good question that came in from Karina Merg. And the question is this: is there a particular book on the history of math that you might recommend? And then a follow-up question for that might be, do you have a source for real-world applications of math, especially geometry, that could be shared with high school students? I think it's
important. So let me think. These are related questions. So
yeah.
So I'm going to start by saying there's a history of math book. It's like more of a pop math book. And okay, I wouldn't, actually, I'm just not going to say what I was going to say, but it's a pop math book, and it does cover like a decent amount of application. And it's, I forget the name of the history book, but it's written by Ball, Ball, maybe Keith Ball. He's over in
Ball.
He's in the UK. He wrote a history of math book. So that, I recall reading that one and sort of remembering that it was quite application heavily, which I think could be useful. And then for a history of math book, let me see. There's Mathematical Thought and something. I recall reading those like a long time ago. It's a 3-part series, and I have them on my shelf back there. I forgot their name, but Mathematical Thought and something. My eyesight isn't what it should be. That 3-part series, I would say, is a really great read for the history of math.
Okay.
Yeah.
Is let's see, the Mathematics Genealogy Project, is that?
No, that's
one
not
you're talking about.
Here, I can
can
even.
I'll keep thinking. We'll keep. We may be able to come back to that.
No, just one search on Amazon, and this will
as you keep.
done.
Oh, you'll have it. All right.
Yeah, I mean, I know the books. I just need to like physically.
You need to see them. That's fair. I mean, this kind of it's really cool. And Karina, I just want to encourage you that you are asking that question, because I think that's really cool to be able to pull that stuff and put it in front of your students to try to excite them about not just mathematics for mathematics' sake, but really why math has come kind of the direction that it's come. Mathematical thought from ancient to modern times is
that's the one. Yeah, that's the one.
Yes. That's the one that Karina just posted in there. And
then the other one that I thought was pretty good is this Mathematics from the Birth of Numbers. This one I read as well. I can't remember what the name of the Ball one was, but I recalled that one was sort of strikingly informal, and the sort of thing where he gave a lot of sort of very down-to-earth examples that I think high school students could relate to.
That's awesome. Well, I just wanted to encourage you, Karina, that man, it's so cool to have those different applications, because looking at where the mathematics we do and learn in high school comes from is important for students to be able to connect to, and it also makes it kind of logical in the way that you develop the mathematics that you know now, right? If you can kind of think about how a particular topic or particular subject has developed over time, it also makes fairly logical sense as to why it did that, and it's also kind of how the way we think, right? So I think that's kind of cool, and I'm really glad you're doing that kind of stuff. I agree. I wish schools would offer a course on the history of math. I think that'd be kind of a cool math course.
Yeah, it's a
or at least
a
elective course that would be kind of cool.
Anytime I talk to a history of like a math history person or a science history person, I'm always like, I would just want to pick their brain. This is like a fascinating area to me, and this is actually like a little bit of a sort of hobby. Like, I enjoy reading these books. Yeah, I don't know. I sort of I kind of see myself like maybe eventually older, I've sort of done a lot of stuff in math, and I'm later on in my career, maybe I really dig into the history of a certain area of math or a time period that I'm very interested in.
That sounds really kind of cool.
No, that's not the name of the book. I don't
it?
think it's Ball. Yeah, I said it was like the last name was Ball, and I thought maybe Keith Ball, but Keith Ball is definitely not the person I'm thinking of. He's a very very well-known sort of convex geometry person. He has a great set of notes on convex geometry.
We're getting some other comments and other questions. If is it this book? Is it this book? And so I'll let those keep rolling in, but I don't know.
Yeah, and I don't think I actually have it on my bookshelf. I think I may have donated it to someone. I think I did.
Yeah. That's okay. I have one more thing that I want to get us to kind of tackle, and that is this. Yeah, and if we do get that later, or if you want to send me that or whatever, we can post it.
Yeah, it's a gray paperback. I forget the name of it. Gray paperback written by a UK author. Yeah.
Okay. Yeah. Okay. So we'll put that in the chat. John, if you get that, you can email it to me and we'll put it in the chat at a later date. So I have one more thing for us to talk about, and then we're going to probably wrap up. And that is, so we did use some technology to help us visualize some things in this series of videos that we talked about. And I just wanted to ask you briefly, maybe if you could talk about, the importance of being able to visualize things, and maybe how technology can help with that. Mm-hmm. And how maybe that deepens the experience for students.
Yeah, no, that's a great question. First of all, I think anytime you can make something visual, it's great. Like for instance, when we did these, we did do some technology stuff, but we also did some stuff like just with, pieces of paper and sliding things. Mm-hmm. And I think that's really important. The main thing I would say is, for things like, translations, rotations, reflections, we can use a piece of paper and we can move that. You don't strictly need technology for that. But when you get into sort of more complicated things, or things that are not so easy to sort of do just without technology really gives you a really good way to visualize things. And I would say this is sort of relevant in even things I do. For instance, I was working on a problem today and I'm trying to get some good intuition about it. And so a thing that I do to get good intuition is I'm working with some function and I say, what does that function even look like? Like I'll pull up whatever technology, I'll plot it so I can look at it, and I'll just play around and I'll slide the parameters a little bit and see how it changes. And yeah, of course, I'm sort of doing a rigorous analysis. I'm trying different techniques. I'm looking, is there convexity anywhere? Is there any sort of nice thing? But at the end of the day, I am also trying to use technology to help me visualize sort of whatever math thing I'm working on, so that I can really get better intuition about it. And I think that's a really important thing. And if you talk to any mathematician or, physicist or, any person in any scientific field, I really think they'll tell you how much modern technology has sort of impacted and helped their field.
That's the truth.
Yeah,
that's the truth. And I think, you hit on it right on the top of the head with when you're thinking about how do I approach something from get a good sense or just kind of a feel for the way things are changing, the impact of certain parameters on my picture or on the problem itself. It's so helpful to be able to just explore just a little bit in ways that you never could with pencil and paper. Yeah, I think that just it just embeds it in our minds, being able to see that. So many of us are visual. Well, John, it's been a pleasure chatting with you this evening. I've learned some things about different books that I may need to go read. So interested in that. So thank you for that. And thank you for the conversation. And man, it was a blast doing these videos.
Yeah, I really enjoyed it. It was a fun time.
All right. Well, with that, I guess we'll sign off and we'll let everyone go have a good evening. So good night.
Good night.